Okay, this lesson will be looking at the kinetic theory of gases, and it would be useful if you'd had a look at gas laws prior to this lesson, and also the ideal gas equation. However, essentially what we're doing in this lesson is we're looking at how the macroscopic, what happens on a very large scale, with particles bouncing around inside a box, and the ideas of volume, pressure, and temperature, and how these ideas on the macroscopic, the large scale, are justified with how particles behave inside the box. And so what we're essentially going to be looking at is going to be looking at how a particle strikes one wall of that box. And we're going to look at a particle of mass m and velocity v. It's going to strike a wall, one wall, though there are many in there. We're just dealing with one wall, one particle, and it bounces back elastically, meaning that there is no loss of kinetic energy. Okay then, let's first of all, let's look at the momentum of this particle initially. Now you know that the momentum is mass times the velocity, and hopefully you'll notice in the second instance, though there's no change in speed, there is a change in velocity and that it's moving the other direction. So the momentum before and the momentum afterwards is now going to be minus mv. So therefore, what's taken place on this wall is you've got a change in momentum, which is the momentum before minus the momentum afterwards. The change in momentum is the difference. In this instance, we have mv minus mv, which suggests that the change in momentum is 2mv. Okay then, we know that, hopefully we can recall, that force is the rate of change of momentum with time. So we have a change of momentum here. We need to work out what's the time period. In other words, how long it takes to strike one wall and then to come back and strike it again, because essentially we will be looking at how it's working in this plane, which has two walls between it. And we're going to say that the distance between those two walls is L. Okay then, so from when it strikes, it bounces to the other side of the box and it bounces back again, it would have covered a distance of 2L. And so therefore the time period, if I just write in what we know to start with, and so therefore the time period is going to be the distance divided by the velocity. The distance in this case is 2L, and divided by the velocity of the particle. Okay, some cancelling can take place, but interestingly the v's cannot cancel because in dividing by a fraction you merely invert it, and therefore we have mv squared over L. Good, now there's a force. But what's interesting is, of course, that we're looking for a pressure, because that's what we've been dealing with in our previous gas laws and ideal gas equation values, pressure. So if we imagine that that wall has an area A, pressure, which is exerted, is going to be the force divided by the area. And we have mv squared over AL this time, which is saying mv squared over a volume. Superb. This is really interesting because we've got a volume now and a pressure, and you can see this is leading us back towards the values that we had in the first instance. However, in all of these cases we've just looked at one particle. Now we need to imagine that we scale this up to look at many particles. So let me just put this equation back together again. P is going to be not just one particle, but many particles. So we need to first of all consider n number of particles. And also, we need to assume that this is not just moving in one plane back and forth. There are 3 planes, and with enough particles statistically, a third will be moving in each plane. And finally, the velocity squared function we have here. We're not going to be looking, because we have more than one particle, of course you've got more than one velocity, so we don't average the velocities and then square it. we're looking to square the velocities first, add them together, and then find the average. So, just an aside, what we're looking at is we're looking at the square of one velocity, then the next velocity, then the next velocity, and so on, and divide it by the number of particles that we have present. Okay, now that's very different to saying we're going to average the speeds and then square the final product of it. In actual fact, if that were the case, then if you average all the velocities, you're likely to come out with 0. So anyway, something to bear in mind. So the notation will be average speed squared. Fantastic. So therefore, that brings us, with a slight rearrangement, there is a very famous equation. And the reason why it's so useful is because it takes the macroscopic world of pressure and volume and it describes microscopically what's happening in order to manifest those gas laws on the outside. Excellent. Now, the last little bit will be, there are a few variations we can have on this equation here. If, for instance, I rearrange, let me do it down here. Let me imagine I rearrange, so I get pressure is a third nm over v squared. Then this function here, which is the total mass over the volume, is actually the density. If you recall, density is mass over volume. So therefore, the pressure is a third rho v bar squared. Another really interesting equation to make use of. And then finally, it's not too hard to see that in rearranging this equation, I can have, let me rearrange it to this form. I bring the 3 up and I move the n down, and that gives me m v bar squared. Now this isn't very far away from the kinetic energy equation, which is a half mv bar squared. So therefore, bearing that in mind, if I put a half on both sides, then effectively I've come out with a kinetic energy. Let me rewrite that down here. 3 PV 2N gives me my kinetic energy. Bearing in mind again that PV is N KT. Do you remember that from the ideal gas equation? And I substitute my PV into this equation down here. I come out with 3N KT over 2N gives me my kinetic energy. With a little bit of cancelling out, I can say to myself, the kinetic energy, the average kinetic energy of a gas, an ideal gas like we're talking about, is 3 over 2 kT. And this as well is really quite interesting because it defines the Boltzmann constant again. What the Boltzmann constant is saying is that for a very simple monatomic gas, which we're dealing with under ideal conditions, K indicates how much energy each particle gains if they gain 1 Kelvin of increased temperature, or indeed decreased temperature. Right, so there are 3 major equations that we're going to be dealing with. Let's make use of them in an example. Here's the first one. Here's the setup. So we have I'll take 1 mole of a gas, hydrogen gas, which has a mass of 2 times 10 to the minus 3 kilograms. In actual fact, that's their molecular mass if I've got 1 mole of it. It has a volume, 2.26 times 10 to the minus 2 meters cubed, and a pressure 1 times 10 to the 5, a normal atmospheric pressure, 1 atmosphere in effect. And the question is, first of all, what is the speed of the particles moving around in that gas? Okay, if you think you know, press pause, give it a go. If not, so we're looking for the speed. If not, I shall show you the answer right now. Okay, there's a little bit of slight rearrangement and description of terms we need to deal with here. So let's just set up the equation that we know. Simple rearrangement gives us 3PV over NN. Now, when we write the final stage, which is the speed of the particles, it comes out, if I square root this side, that's not actually square rooting, that doesn't give us V, mathematically that doesn't give us V. That gives us the square root of the mean squared speeds. We could go into the maths and explain why, but let's not worry too much about it. So what we call it is the root mean squared, so we call it the VRMS value. We need to be careful to describe that it is that, because we're dealing with averages overall, and in gases you're going to have a complete range of speeds, but we're taking the most likely speed, etc. Okay, let's substitute in some values for this. 3 times 1 atmosphere times the volume, and then divided by, now careful about this here, that n is the mass of one particle. This n is the whole number of particles we've got present. So really what this indicates, this whole part here, is the total mass of the gas. In this case, my 2 times 10 to the minus 3. And I square root that, giving me 1841 meters per second. It's pretty fast. But if you look at this proportionality, the lighter the gas, the higher the speed, and vice versa. Okay then, now, the second one was going to be, I'm going to take a random gas. So this was part A. Part B, I'm taking a random gas which has a molecular mass of 0.22 kilograms per mole. It's got a temperature of 273 Kelvin, and I want you to work out the V RMS. If you think you can do it, give it a go. Hit pause and try it. If not, then I'm going to run straight into the solution straight away. Okay, now there's a slight change that we need to consider here, in that PV, which is a third NM V bar squared, is also equal to nRT, because this was our original identity for the gas laws. So the temperature could dictate the same for the speeds as well. So taking this part of the equation here, and ignoring the PV this time, I'm going to say a third NM V bar squared nRT. We have 1 mole of a gas, so this is obviously goes to 1. Let me rearrange first so I can describe it a little bit more. 3 lots of it, divided by NM, and square rooted. Oh, that's a little cramped there, no matter. Obviously 3, we can't change that. This is 1, because we've got 1 mole of gas. 8.314 is our gas constant, and we're at 273 Kelvin. Important to keep that in Kelvin. And the total mass present, and because I've got 1 mole, 0.22 per kilogram. Keep everything in standard units. And that gives me 175 meters per second. So a pretty slow gas in this instance. Excellent. Time for one more example, I think, before we finish this off. Okay, I have bromine gas. And we're looking at how bromine gas diffuses. So, bromine, which has a molecular mass of 0.16 kilograms per mole, we are going to put it at a temperature of 273 Kelvin, and we want to work out from that its speed again, the RMS. Once again, if you think you can do it, go for it. Hit pause and give it a go. If not, I'll go through the solution right now. So we go from very much the same stance as we did before. We know that the kinetic energy, which is a half mv squared, is 3/2 kT, and we would then say that my VRMS is going to be 2 lots of the kinetic energy divided by n, and square root the entire thing. Not as easy as it first seems, but let's go for that twice. That's right, we're going to do twice the kinetic energy, so 3/2 times the famous Boltzmann constant times the temperature, and divide that by the mass. Now, interesting point here. The mass is not the mass, the total mass, but we're looking at the mass of one individual particle. So, what we need to do is, we need to find out somehow, with our molecular mass here, what the mass of one particle is. Okay, I think that's fairly straightforward. The molecular mass divided by the number of particles in a mole will give us the mass of the one particle. So, 0.16 divided by 6 times 10 to the 23. And that gives us 2.7 times 10 to the minus 25, I believe, kilograms. So if we just jump back to the original equation, and now introduce the mass, and square root it. Forgot to put that sign in before, just to keep everything consistent. That brings us to 212 meters per second. Now, there might have been a faster way of moving from this stage straight through, but I wanted to show you each step as we go. Okay, hope that all makes sense.